Hello everyone, my name is Yijie Zhou. The title for my presentation is Adaptive Linear State Estimation for Unbalanced Distribution System. First, a brief introduction about myself. I got my bachelor's degree from Huazhong University of Science in China and my master's degree at University of Southern California. I'm currently a PhD student under Dr. Centino. My research interests include wide area measurement, state estimation, and signal processing for power systems. This slide shows the topic I'm gonna cover in this presentation. Firstly, I will start with the introduction and motivation of this research. Secondly, I will talk about optimal PMU state placement strategy for unbalanced distribution system. Thirdly, I will talk about adaptive linear state estimation for unbalanced distribution system. Lastly, I will conclude the presentation with simulation result and a summary. First, the introduction. What is linear state estimation and why do we need to study it? State estimation is the mathematical tool that aims at estimate the most probable system state in the presence of measurement errors, communication noises, and telemetry failures. The formulation of the estimator depends on the type of measurement used as input. If traditional magnitude and power flow measurement from the SCADA system are used, then the formulation of the state estimation problem is nonlinear and requires iterative solution. When using synchronized measurement devices such as PMUs, the formulation of the problem becomes linear, hence the name linear state estimation. Linear state estimation is fast to solve and free of convergence issues. The synchronized measurement also enables the estimator to provide a real-time snapshot of the system state, which is essential for various power system applications. While linear state estimation has been widely proposed and has already seen some implementation in high-voltage transmission systems, its implementation in distribution systems is still an ongoing research topic due to difficulties unique to distribution systems. The first common issues in distribution system is the low level of observability. To solve this issue, some researchers propose incorporation of pseudo measurements such as low power consumption inferred from the previously acquired information. However, these measurements are non-real-time and have high variance, which affect the accuracy of the estimation process. Nowadays, with lower cost and increased access to commercial communication channels, synchronized measurement devices has become more affordable and accessible to distribution systems than ever before. Reliable linear state estimation can be achieved in the near future. Another common issue of a typical distribution system is the unbalanced structure of the system. In transmission systems, the lines are often assumed to be transposed and equally loaded, which make it possible to combine the self and the mutual inductance of a line into one equivalent inductance. And positive sequence voltage can be used as the state variable of the system. However, in distribution systems, there are single-phase, two-phase, and untransposed three-phase lines serving unbalanced load, which make it necessary to account for the phase coupling of the lines and use the phase voltages as state variables. This is something we address in the proposed linear state estimator. For a state estimator to be able to estimate the state of system, the system first needs to be completely observable. It is also Ideal to achieve this, use minimal amount of synchronized measurement so that it is cost-friendly. The goal of the optimal PMU placement scheme is exactly that. Assuming a PMU placed on a bus measure a bus voltages and the current of all the lines that are connected to the bus. The traditional scheme proposed for the transmission system can be defined as shown in this slide, where X is the binary placement vector that indicate the optimal PMU locations, and A is the bus incident matrix, whose definition is also shown here. It contains the information of which buses are connected to each other. However, this scheme may not be able to guarantee complete observability for unbalanced distribution system because it does not consider the two-phase and single-phase buses that may present in a distribution system. For example, for this simple three-bus system, to make bus 1 observable, the transmission system scheme can choose either bus 2 or bus 3 as the location for the PMU. However, we can clearly see PMU on bus 3 does not grant complete observability of bus 1, since only one phase of bus 1 can be inferred from the measurement it provides. To solve this issue, we modify formulation of the A matrix and the corresponding constraints to make sure PMUs are more likely to be placed on buses with a greater number of phases, so that all phase voltages of all the buses in the system can be estimated. It is also necessary to monitor topology changes in the system to ensure robust performance of the estimator. This can be achieved by constructing another line-to-bus connectivity matrix B to ensure all lines current are monitored. This slide shows the widely proposed linear state estimator for a balanced three-phase transmission system. The Z and X vector are the measurement vector and the estimated state vector. The H matrix is the measurement matrix that relates measurement to state variables. The E vector is the measurement error vector. In a balanced three-phase transmission system, the self and the mutual inductances can be combined into one equivalent phase inductance, so the system can be reduced to a single-phase equivalent and the positive sequence voltage can be used as state variable. However, in a distribution system, there are two-phase, single-phase line and untransposed three-phase line serving unbalanced load. Therefore, the mutual inductances of a line need to be modeled separately. For the three-phase line, it can be modeled as a 3x3 line impedance matrix. For two-phase and single-phase line, one or two rows and columns are removed to form a reduced impedance matrix. In distribution system, phase voltages need to be used as state variables. Topology tracking is also very important for estimator designed for distribution system. Since topology changes happen frequently in distribution system due to fault, load transfer, or just some troubleshooting operations. In this work, topology changes are tracked by reading the breaker status monitored by extra PMU placed on either end of each line. If the system is still observable after the topology changes, then after removing the effective measurement from the H matrix and the Z vector, the estimation process can continue. If the system becomes unobservable after the topology change, then the unobservable state need to be removed from the X factor so that the estimator will not output any error. This method can be extended to tracking bad data, but specialized algorithms need to be used for bad data detection and identification. The performance of the proposed PMU placement scheme and linear state estimator has been verified by simulation on the IEEE 13, 34, and 123 bus system. Due to limited time, only results from the 34 bus system are shown. From the table shown in the right, we can see that the transmission system OPP scheme does not provide enough measurement for the 34 bus system to be observable, while the proposed OPP scheme achieves complete observability of the system using the same number of PMU as the traditional one. The performance of the estimator is verified by calculating the total vector error of the estimated voltage phasors, which is a common metric used to evaluate the performance of PMUs. It can be seen from the graph that the estimator achieves high accuracy with the highest total vector error below 0.05%. The noise rejection performance of the estimator has also been verified by imposing Gaussian distributed random noises on both the voltage and current measurements. The noises are assumed to have zero means and 0.01 variance for the voltage measurements and 0.03 variance for the current measurement to account for the fact that the current measurements are generally less accurate than the voltage measurements. From the graph shown in this slide, we can see the estimated state can converge to the true states in the presence of random errors to some extent without introducing any bias. The performance improvement of adaptive estimation over traditional estimation has been verified by fault simulation in Simulink. In the scenario shown in this slide, a three-phase to ground fault is inserted between bus A36 and bus A40 at 0.49 seconds and clear at 0.55 seconds. The protection system detects the fault and the breakers on both sides of the faulted line trip at 0.5 seconds and recloses at 0.6 seconds after the fault is clear. From the graph shown in this slide, we can see that apart from the transient period caused by the fault and the breaker operation, the adaptive estimation scheme with topology tracking have far less estimation errors than traditional estimation process using fixed formulations. This brings us to the conclusion. The main contribution of this work are threefold. Firstly, we developed an adaptive linear state estimator for unbalanced distribution system. The estimator can adaptively change its formulation to account for system topology changes. Secondly, we developed a modified optimal PMU placement scheme that can guarantee complete observability for an unbalanced distribution system. Thirdly, we verified the effectiveness of the linear state estimator and the proposed PMU placement scheme on the IEEE 13, 34, and 123 bus system. That concludes my presentation. Thank you for listening.